Hello, everyone. Welcome to our presentation on customized facial expression analysis in video. I'm Dominic, and this is joint work with Apu, and we represent Mobius Labs, a Berlin-based startup working on providing computer vision solutions for a wide range of applications. And one of the main features that we work on is customizability. And today we'll see how we achieve customizability for facial expression analysis. First off, I would like to point out that while often confused or used interchangeably, emotions and facial expressions are not the same thing. So emotions are the things that we feel, and facial expressions, they refer to the positions and motions of muscles beneath our skin. So while they can be an indicator of an emotion we are feeling, they do not always reflect an emotion. So for example, I can be smiling, but actually be sad, feeling a sad emotion. So let's get started with some previous work on emotion classification. So basically, most of the existing AI systems, they are trained to identify 6, sometimes 7 basic emotions that were identified by Paul Ekman, who has been working in this field for over 40 years. And yeah, they basically have these emotions that you see below. So anger, contempt, disgust, enjoyment, or often referred to as happiness, fear, sadness, and surprise. And then these models just take a face as an input and output the probability that a certain emotion is being displayed. The problem with such approaches is that adding new classes requires a lot of training data. So whenever you want to add a new emotion, it basically requires you to retrain the entire model, which is very slow and also very difficult to sometimes to find enough training data. Another interesting approach is a facial action coding system called FACS. And this was actually developed in the late 70s, proposed again by Ekman and Friesen. And this was initially used to train humans to identify emotions. And how it works is the FACS specifies 32 atomic muscle actions, facial muscle actions, which they call action units. And so we can, for example, then take a happy face, and we will find that there's 3 action units that are active, namely AU6, which is a cheek raiser, so the cheeks are up, and then a AU12, which is the lips corner puller, and so on. More recently, the Du et al., they propose to merge these action units to come up with new emotions. So you can, for example, take action units from a happy face and those of a surprised face, and you get a new emotion, which they call happily surprised. And in their work, they identify 21 new merged emotions. However, as they also mention in the paper, they only can show that a human can actually distinguish between these newfound compound emotions, but they're actually not able to train a system that can differentiate between them. And they also mentioned that it's really difficult to get enough training data. The last work I'd like to present is called facial expression comparison. So rather than defining specific action units and collecting data to train those, the work by Vemulapalli and Agarwala is basically using deep learning to learn facial expressions by taking a lot of triplets of face images and asking human annotators to say which one of the 3 faces in any given triplet is the most different from the 2 others. So as you can see in the triplet 1, all 3 faces, they're smiling, but the 2 ones on the left, the smile is a bit bigger than in the one on the right. So the one on the right probably would be marked as the most dissimilar expression. So this work is basically what we used as inspiration, and we also used the data set that was proposed here to train our model. So now for the first part of our actual technical proposal, let's have a look how we learn to distinguish facial expressions. And I'd like to start with a kind of a mental picture of what we're trying to do here, which will follow us through the presentation. So imagine you're sitting at your table at home and you have a pile of photographs of people with different facial expressions, and you want to sort them according to the facial expression. So you would start placing the first photograph and the second one, and then you keep on doing this, always trying to put similar facial expressions closer to each other. And as you're doing this, you will find that maybe in the top left, you have like smiling people, right? And then as you go a bit more to the center, the smiling gets a bit less pronounced, and it even turns a bit into a sad face. And then if you go even more on the right, you have like people with their mouths open. And personally, I would label those as maybe surprised or excited. And if you go to the top right image, the person is kind of exhibiting an angry face, right? So what is interesting now is you could place a ruler onto the table, and you could measure the distance between different photographs or different facial expressions, right? So facial expressions that are more similar have a smaller distance, and this notion of distance is going to be very important for our work here. So the question is, how can a machine measure distance? Because it cannot lay these photographs onto a table, right? It has no notion of facial expressions to start off with. So what we do basically, and I call this from face to expression fingerprint, is we take an image, we extract the face, and then we run it through a neural network. This is a convolutional neural network, like they're used for a wide variety of applications. It has as input a crop of a face, and then it has what we call a facial expression embedding network, FENet, which outputs a feature embedding vector. So this embedding vector is what I call expression fingerprint, right? And if you just take this model initially, it has random weights. So there's millions of parameters in there, and they're randomly initialized, and it has no idea what a facial expression is. So this feature embedding vector will just be random numbers. But what we can do now is we can take these triplets of images that I showed before and feed them into a training of the facial expression network. And we use what is called a triplet loss, which basically says, well, the two facial expressions that are more similar, they should have a smaller distance. And now if you recall from high school geometry, if you have a vector, you can measure the distance between this one and another vector. And in the training, we basically say, if the distance between the two facial expressions that are more similar is larger than they are to the third expression, which is more dissimilar, then we actually adjust the weights in our network just a bit, so that the next time when we have a triplet that looks similar, we basically have a better prediction. And if we do this over and over and we keep on training, we basically start getting features that make more sense, right? And we can, for example, then look at trying to interpret what the system learned. And this is just an example, right? We're not explicitly encoding anything, but what we find is that the embeddings actually do have specific elements in the vector that encode a specific feature. So for example, the first element could be how open the eyes are, right? And if the eye is closed, the value would be -1. And if the eye is fully open, it would be +1. So as you can see in this example here, we would have the two images on the left. they would have, like they have kind of closed eyes. The one in the middle is kind of a little bit open, so it would be negative 0.7. Whereas the image on the right, the eyes are quite open, so it would be maybe 0.9. And the same goes for all these different elements in that vector. They all have certain meaning. And the good thing is we don't have to explicitly encode action units, right? It's just what the system is using to distinguish different faces. Over time, it will find that eyes are important, that cheek positions are important. So that's a very elegant way of actually solving this problem of learning to distinguish facial expressions. Now, how well can we actually distinguish facial expressions? One way of measuring this is we can take a left out set of triplets. In our case, it's around 10,000 triplets that we use for evaluating the system. So the system has not seen those during the training, but we can use those now and say, well, how many of these triplets is our system actually correctly classifying, meaning that the two more similar facial expressions have smaller distance. So if we do this, we find that we actually get a triplet prediction accuracy of around 84.5%. Compared to the previous work, which was at 81.8, there's an improvement. But personally, I find much more interesting that if you look at the average human performance, we actually are very close, right? So an average human has an 86.2% triplet prediction accuracy. So basically, we can say that the proposed FeeNet is almost as good as a human at distinguishing facial expressions. And if we now take these embeddings and we project them onto a two-dimensional space, so this comes back to this analogy of the table, this is what our trained system now thinks these facial expressions can be organized by. So if we start zooming in, we will find in the top left, there's like happy faces, smiling people, right? Which would be mostly, we would say, well, they look happy. Then you have in the top right, there's people with their mouths open, and maybe you would call that surprised, expression. And then in the bottom here, you have neutral faces. And what is very interesting now is we can zoom in, for example, on the happy cluster. And we see that the system is able to not just say, here's somebody looking happy or smiling, but we have a whole range of happiness. And so this is basically evidenced in this slide where you can see that in the top row, we have a very light smile. So all the images that I show here, they basically have very, very small distances to each other, meaning that the system will say, well, they're the same facial expression. And we can do this for every row. You see, as we go down, there's more and more the mouth corners go up. So the system kind of learned without explicitly knowing that there's something like smiling, right? So that's a very nice feature of this. So very fine granularity of facial expressions that we can distinguish. And then the last part is how can we add custom facial expressions is now as simple as taking one face that displays the facial expression we're interested in, and it will we add this to the database, and then we can here we visualize if we compare this face and compute the distances to around 10,000 faces, what you see is the closest matches. And you can see that they're all looking very similar, which means that the system really learned to distinguish these facial expressions. All right, so let's shift gears and see how we can use this on videos. For videos, one of the main challenges is that typically video frames, so frames we extract from videos, have lower quality than just a photograph, right? And that's partially, you have motion blur, which makes faces a bit blurry. You have compression artifacts, which are a lot more prevalent in videos than they are in images. So we need an automatic way of filtering out low quality faces. And in this paper, what we propose is an automatic face quality assessment box, which basically assesses two things. One is how sharp is the image, And the second thing is how sideways a face is. You know, frontal faces are the easiest. And as you keep on turning your head, you get more and more sideways. And if a face is too much at an angle, it's very hard to actually distinguish facial expressions for a human already, but also for a machine, because we simply don't have enough training data for very sideways faces. So that's what this automatic face QA box is doing. More details are in the accompanying paper. But what is important here is that we reject sideways and blurry faces, and we're left with a pool of accepted faces. In the next step, we group these faces into different identities, because in order for a meaningful facial expression analysis, we need to have each, like we can only do this per person. You know, it doesn't make sense to compare facial expressions across people in a movie. So we do this using face features from a face verification system, which has been taught trained to learn, distinguish different people. And if we now put this all together, so we have, on the one hand, we have this custom face expression database. In this example, there's just 3. So we add these 3 faces to the database, extract the facial expression embedding. And then we take, for example, the main actress of a movie, and we sort the extracted faces chronologically, right? This comes from a movie, so we have a timeline to it. And then for each of these faces, we extract the facial expression embedding. And then for stability, we have a temporal pooling part where we look at nearby facial expression embeddings and compute an average. So that kind of filters out if there's some, if you know, in one frame, somebody has their eyes closed, but in the others they're open. So this stuff gets filtered out, which just gives a better facial expression tagging. And then whenever we have a match with one of those pooled facial expression embeddings, so if the distance is close or small, rather, to one of the reference faces, we assign it that emotion, that facial expression. All right, now let's get to the fun part, which are the applications. The first one is we can track custom facial expressions. So for this, we took an article by a psychologist who identified 7 typical faces of Donald Trump. So we went into this article, we took the photographs from that article, extracted the faces, and used what was assigned as a expression tag from the article. So you see those at the top of the plot. And then we took a roughly 2 hour long presidential debate between Donald Trump and Joe Biden, and computed the facial expressions for all the faces. As you can imagine, there's thousands of faces per identity. What we show here is now the top matches for each of these different custom facial expressions. Now, you might be wondering, well, okay, so I see that Joe Biden has this exaggerated mouth, but how often does he display that part, right? So we can, of course, now count how many times people show a certain facial expression, and we can plot this. So what we show here is for Trump in red and for Biden in blue, what's the rate of appearance of a certain facial expression. So we can see that Donald Trump has around 20% of the times he's in this exaggerated mouth facial expression, whereas Joe Biden was smiling a lot more, right? Because his big smile is almost at 20%, whereas Donald Trump almost hardly smiled at all. So this is all done completely automatically. And I would like to end this talk with a more playful application, which is what we call facial expression summaries. So instead of taking close by facial expressions, we can also sample from all over the facial expression range and then display it. So here we show for Jim Carrey, the kind of the master of facial expressions, We extracted from multiple movies. We extracted all his faces, and these are the top 15 facial expressions that he exhibits. All right, that concludes the talk. If there are any questions, please do not hesitate to send me an email. We're always happy to discuss things. You know, if you have ideas on how this could be useful for you or suggestions, very, very welcome. Also, please do visit our website, mobiuslabs.com, and we also have a presence on Twitter and on LinkedIn. All right, thanks a lot, everyone. Bye-bye.